The first colonizers to Mars could forge a schism in the species, one that makes physical contact with Earth-based humans lethal. I don't think there has been nearly as much discussion about what would become of the people that are living in these colonies generations later, says Scott Solomon, a professor at Rice University. As humanity sets its sights on colonizing Mars, one of the lesser-known challenges that may arise is the potential risks associated with physical contact between Mars colonists and Earth-based humans. This issue stems from the stark contrast in environments between the two planets, particularly the sterile conditions that Mars colonists would be living in. Mars, with its harsh and inhospitable environment, poses unique challenges for human habitation. Colonists would be living in enclosed habitats, carefully monitored and controlled to maintain a sterile and safe living environment. This strict hygiene protocol is essential to prevent the introduction of harmful pathogens or contaminants into the delicate Martian ecosystem. In contrast, Earth-based humans are exposed to a wide range of microbes and bacteria on a daily basis, building up a diverse immune system capable of fighting off various pathogens. The potential risk arises when these Earth-based humans come into contact with Mars colonists, who may have weakened immune systems due to living in a sterile environment. Any physical contact between Mars colonists and Earth-based humans could potentially introduce harmful pathogens to the Martian environment, leading to the contamination of habitats and jeopardizing the health and safety of the colonists. This risk underscores the importance of strict quarantine protocols and thorough medical screening for any individuals traveling between Earth and Mars. As we venture into the unknown frontier of Mars colonization, it is crucial to address the challenges of interspecies physical contact and to develop robust protocols to ensure the safety and well-being of all individuals involved in the mission. Mars holds great promise for the future of humanity. It is essential to consider the potential risks associated with physical contact between Mars colonists and Earth-based humans. By implementing stringent hygiene protocols and quarantine measures, we can mitigate these risks and ensure a successful and sustainable colonization effort. It was perhaps one of the most bizarre revelations about the plans to build cities in outer space. Elon Musk's SpaceX is rushing to establish a city on Mars by 2050, using its Starship rocket and competitive ticket prices to encourage punters to come along for the ride. Jeff Bezos' Blue Origin is focused on building floating, orbiting space stations that make it easy to return to Earth while creating outer worlds. In SpaceX's case, the goal is to establish a planet-hopping species. The Starship is designed to run on liquid oxygen and methane, harvestable from many planets. Astronauts could set up a propellant depot and send the Starship out even further, or return home to Earth. Unfortunately, thanks to an accelerated mutation process and unique living conditions, those Mars humans may not last long on their return to Earth. Despite what many think, genetic adaptation is still playing a part in modern humans. That would be accelerated when humans go to Mars. If a mutation gives humans a 50% greater chance at survival, that's going to rapidly skew the number to favor that benefit. And while most kids are born with 20 to 120 mutations, high levels of radiation could cause that figure to surge. What might those changes look like? Think more nearsighted people adapting to confined spaces, more efficient use of oxygen, denser bones to counteract Mars' 2/3 weaker gravity, and possibly a new skin tone better suited to the radiation. The most radical change could be the loss of an immune system. That's because the humans would live in a sterile environment, which could mean immune systems wither away over time. Ships between the two could act as a quarantine zone. As the two groups no longer intermingle as much as before, there could be a rise in nationalism, new economic thought, and perhaps a class divide. Getting humans to Mars? It could be the least of our worries. In the quest to colonize Mars, humanity faces a unique challenge that often goes unnoticed: the potential risks of physical contact between Mars colonists and Earth-based humans. Mars, with its harsh and sterile environment, requires colonists to live in enclosed habitats with strict hygiene protocols to prevent contamination. In contrast, Earth-based humans are exposed to a multitude of microbes and bacteria, building robust immune systems over time. When these two worlds collide, the risk of introducing harmful pathogens to the Martian environment becomes a significant concern. To address this challenge, stringent quarantine protocols and medical screenings are essential for individuals traveling between Earth and Mars. As humans embark on the journey to colonize Mars, ensuring the safety and well-being of all individuals involved is paramount. Mars colony will most likely have focus on the importance of safety and hygiene practices. Humanity has sent around 30 spacecraft and landers to the Red Planet since the space age began. Now, we know which microbes might have survived the trip. NASA and its engineers in the Jet Propulsion Laboratory, JPL, have precise and thorough protocols to minimize the number of organisms that might inadvertently hitchhike on a space mission. Internationally agreed standards guide how rigorous these protocols should be, and NASA meets, and in some cases, exceeds them. Yet, two recent studies highlight how some organisms might survive the cleaning process and also the trip to Mars, and also how fast microbial species can evolve while in space. First, let's start with the process that was required to build the Perseverance rover, as well as most spacecraft made in JPL's Spacecraft Assembly Facility, SAF. Their spacecraft are painstakingly built one layer at a time, like an onion, with everything cleaned before it is added. These methods limit the bacteria, viruses, fungi, or spores on equipment to be sent on a mission. Spacecraft undergo rigorous cleaning as they are assembled and prepared for launch to other planets. Spacecraft undergo rigorous cleaning as they are assembled and prepared for launch to other planets. Spacecraft are built rooms with air filters and strict biological control procedures. These are designed to ensure that only a few hundred particles can contaminate each square foot, and ideally no more than a few dozen spores per square meter. But it is almost impossible to get to zero biomass on a spacecraft. Microbes have been on Earth for billions of years, and they are everywhere. They are inside us, on our bodies, and all around us. Some can sneak through even the cleanest of clean rooms. Clean rooms might serve as a genetic selection process for the hardiest bugs that then may have a greater chance of surviving a journey to Mars. Since we can now sequence all the DNA that is present in the clean rooms, and not just the ones that could be cultured, we get a more comprehensive look at what kind of microbes can be found in the clean room, and if they could even survive the vacuum of space. Clean rooms might serve as a genetic selection process for the hardiest bugs that then may have a greater chance of surviving a journey to Mars. Since we can now sequence all the DNA that is present in the clean rooms, and not just the ones that could be cultured, we get a more comprehensive look at what kind of microbes can be found in the clean room, and if they could even survive the vacuum of space. Forward contamination is undesirable from a scientific perspective too. Scientists need to be sure that any discovery of life on another planet is genuinely native there, rather than a false identification of an alien-looking, but Earth-grown, contamination. Microbes could potentially hitchhike their way to Mars, even after pre-launch cleaning and exposure to radiation in space. Their genomes may change so much that they look truly otherworldly. We have recently seen that novel microbes have evolved on the International Space Station. Although NASA's engineers work hard to avoid introducing such species into the Martian soil or air, any signs of life on Mars would have to be carefully examined to ensure it did not originate here on Earth. Not doing so could potentially spark misguided research into the universal features of life or Martian life. Microbes carried into space can also be of more immediate concern to astronauts, posing a risk to their health and perhaps even causing life support equipment to malfunction if they become gummed up with colonies of microorganisms. But planetary protection is bidirectional. The other component of planetary protection is avoiding backward contamination, where something brought back to Earth presents a potential risk to life on our own planet, including to humans. This is the theme of many science fiction movies, where some fictional microbe threatens all life on Earth. But when a NASA and the European Space Agency, ESA, mission is launched towards Mars in 2028, it could become a very real consideration. If all goes according to current plans, the Mars sample return mission will bring back the first Martian samples to Earth in 2032. Past studies have indicated that Mars samples are very unlikely to contain active, hazardous biology, and Perseverance is looking for any signs that might have been left by ancient microbial life on the planet. But NASA and ESA say they are taking additional precautions to ensure all samples returned from Mars will be safely contained in a multi-layered isolation system. There is a chance, however, that if we do detect signs of life on Mars, it could have come from Earth in the first place. Ever since the first two Soviet probes landed on the Martian surface in 1971, followed by the US Viking 1 lander in 1976, there likely have been some fragments of microbial, and maybe human DNA, on the red planet. Given the global dust storms and trace amounts of DNA that might have gone with these spacecraft, we have to be sure we don't fool ourselves that the life we find isn't originally from Earth. We have ways of telling it apart from any life that is truly Martian in origin. Hidden within the DNA sequence will be information about its provenance. An ongoing project called Metasub, Metagenomics of Subways and Urban Biomes, is sequencing the DNA found across more than 100 of the world's cities. Researchers from our lab, Metasub teams, and a group in Switzerland have just published these and other global metagenomic data to create a planetary genetic index of all sequenced DNA that has ever been observed. Even if our exploration of the solar system has inadvertently carried microbes to other planets, it is likely they will not be the same as it was when it left the Earth. The trials of space travel and unusual environments they encounter will have left their mark and caused them to evolve. If an organism from Earth has adapted to space, or Mars, the genetics tools we have at our disposal could help us figure out how and why the microbes changed. Eventually, humans will set foot on Mars, carrying the cocktail of microbes that live on and inside our bodies with them. These microbes too will likely adapt, mutate, and change. And we can learn from them too. They may even make life on Mars more tolerable for those who go there, since the unique genomes adapting to the Martian environment could be sequenced, transmitted back to Earth for further characterization, and then utilized for therapeutics and research on both planets. Given all the planned Martian missions, we are at the shore's edge of a new era of interplanetary biology, where we will learn about adaptations of an organism on one planet and apply them to another. The lessons of evolution and genetic adaptations are inscribed in the DNA of every organism, and the Martian environment will be no different. Mars will write its new selection pressures on organisms that we will see when we sequence them, opening an entirely new catalogue of genetic literature. Thank you for taking time out to watch our video. Please like, subscribe, and share.